Section 1.6, graphical transformation.
Okay, now this is the root of everything we're going to do this year.
Okay. We've been saying that on like every section.
For real.
For real though. Okay, we're going to use all the stuff from 1.2 in a way. Like 1.2 is super
But this
important.
stuff, translations of graphs.
It's a big deal because guess what? If you know your 12 basic functions from 1.3 and you understand the way these transformation rules work, you can graph anything you want without ever having to pick up your calculator.
Double Stampsies to infinity and beyond.
Okay, so that means you agree.
I totally 100% agree.
Okay, awesome. So here's some different vocabulary words real quick. A
Okay.
rigid transformation means you don't change the size and shape of the graph, you just move it. You just like move it.
I'm rigidly moving out of the picture.
Right, but
rigidly moving in, but I
yeah.
don't change my position at all.
No,
I just am tilted.
size and shape. You change your position,
size and shape, yeah.
not size and shape.
But I'm still squeezed in together, fist right here. My shape hasn't changed.
Right. So
Okay.
that's
My
like
shoulders were hurting.
yeah, vertical and horizontal shifts and reflections. Could you reflect across the x-axis for us real quick?
I need a split pick for that. If I had split pick, I could do it.
Okay.
All right.
Non-rigid transformations do the opposite then. They actually change the size or shape of a graph so that, you know, like if he could just get like bigger, like all of a sudden.
Like if you look
in
at my
Harry
head
Potter,
now, and
Aunt
you look at my
Marge,
head now, I'm bigger.
That was a stretch. Yeah.
That was a stretch.
Yeah. Okay, so vertically and horizontally, we can talk about stretches or shrinks.
Or the bus on Harry Potter. Was that where you're headed?
No, I was talking about Aunt Marge, when Aunt Marge blows up.
Oh, yeah, yeah. But
she was
you've also
both
got,
vertically and horizontally stretched.
she was. Or
The night bus.
The night bus.
Shrinks.
When it shrinks to go in between the cars.
Yes, lots of Harry Potter references today. All right,
Yes.
Translations. You can translate vertically, which is up and down. You can translate horizontally, which is left and right. And the important thing to know is every single time you do this, these rules will happen. So every single time. So if your number, okay, we have this f of x thing here. So f of x can be things like x squared.
Oh, that's x squared. That's
okay?
the basic function right there. That's what f of x is
F
our
of
basic
x
function.
could be absolute value of x.
Yep. Oh, hey.
F of x could be
sine x.
sine of x. Okay, this is what we're talking about when we say f of x. There's going to be some kind of actual function there. And so whenever we talk about being outside of our function, we're talking about there's going to be a number out here somewhere. You know? That if, you, like for absolute values, there's an obvious inside and outside, I think. Inside, the absolute values is inside.
Right.
Outside is outside.
Right.
For some of these other ones, you're looking for parentheses.
Right. Like on x squared, there would be a parenthesis.
If you're inside.
If you're inside.
But if there's no parentheses, you're outside.
Same thing for the sine.
Yeah,
so it
this
just
is
depends.
outside.
You'll start to catch that.
That kind of thing, yeah.
Right.
So if we're adding something outside of our function, we go up because we're directly affecting our y values.
Right. Because
Okay.
f of x is equal to y.
Yes.
So if we're saying f of x equals x squared plus 3,
Yeah,
then that
we're
means
taking-
the y is affected plus 3.
That's right. If we subtract c, the opposite happens, and we
Right.
shift down however many
Exactamundo.
the c units are. Horizontal translations, what you have to remember is anytime we're inside of a function, we are in the super secret opposite society.
Every single time, the
Okay.
SSOS.
Okay? If you can remember that, that means that anything that happens inside of your function, the opposite is going to happen than what you think. So if I subtract c on the inside,
I'm actually going to move in a positive direction
Which
on
is
the
to
x-axis.
the right.
That is correct.
Okay? If it's a plus c on the inside,
We're moving in the opposite direction.
which is left c units.
That's
Okay?
correct.
So when we're outside, we're not a part of the society, but when we're inside, we're a part.
Super secret.
The super secret opposite, because we're going to change it to the
That's right,
opposite
that's right.
society. Okay, so
Thank you,
let's
Mrs.
do
Golden, for that reference,
Yeah,
by the way. We'll
yes.
give credit where credit is due,
sometimes.
usually.
Okay, so let's do an example.
Hey,
of
let's
this.
do it. Hey, look, that looks like absolute value
Of x.
of x. Yes,
Okay,
just of x.
y equals the absolute value of x. So our parent function is the absolute value function.
Right.
And we're trying to describe how the graph of this can be transformed to the graph of the given equation. So what matters...
It looks to me like that -4 part is not inside the
Right.
absolute value.
Right, this is outside, which means it's affecting our up and down. Since it's negative, it's legit pulling us down
Right,
4.
right.
So we would write that we are shifting down 4. or shift down 4 or something to that effect. And
4 units.
You don't have to put units. I mean, you can.
We didn't put units here, but it would be some sort of unit typically.
You could put units or you could not. So.
Okay, all right, so quick pause. So let's take a look at the graph then.
Okay, without using our calculator.
Yeah. Oh, okay. And graph the parent function first.
Okay, so in pink here, I know the absolute value of x.
I do too.
It's a v.
Yes.
With like, if you imagine slopes of 1 going both directions.
No, not slopes of 1 going both directions. A slope of negative 1 and a slope of 1.
My apologies.
Get your vocab correct.
So
we got that mistake on film.
Yeah.
I'm gonna ride that one.
Now, all we're doing is taking this parent function and moving it down 4. So
4 units.
Uno,
1,
dos,
2, 3,
tres,
4.
cuatro, and then otherwise it should look the same. Like we should have like a parallel line situation going on, which I am freehanding, so I mean it looks okay.
I mean it's not bad.
Okay, but that's all that happened. We just took what we had and we moved it down 4.
Took all the y coordinates down 4.
Okay,
all right.
So let's do the next one.
Okay, notice now on this one, like Mrs. Stevenson said on our opening slide, we've got that 2 on the inside of the absolute value, and it is obviously on the inside.
It is in the inside, right. It's inside of our absolute value bar. So this is a part of the super secret opposite society. So instead of +2 taking us to the right 2, it actually takes us to the left 2.
Left.
To the left. To the left. Everybody go to the left. Left
Hey, isn't
2.
there a song?
There is a song about that. Shift left 2.
No, that's not the name of the song.
No, that's not. You're
Okay.
right. And you don't have to write units, but if you want to, you can. So let's graph. Let's think about what the graph looks like then.
So we're going to, again, start with the absolute value graph, which is the V.
A V for victory.
That's right. V for vociferous.
What does that have to do with
I don't
anything?
know.
Okay.
Now, that whole
Left
thing
2.
is going to go not right 2 because it says +2, but actually the opposite of that, which is left 2, and then it's an identical replication of the graph.
You're just picking it up and moving it.
Boom.
Okay.
So you can reflect these puppies.
Across either axis.
Either way.
Okay. Across the x-axis, what's happening when you reflect across the x-axis? You make the y's negative.
Yeah, notice, y values go up. So if I reflect over the x-axis, instead of y values up, y values down.
Okay, so it just changes those signs. What it looks like in our function notation thing we've got going on here is that the negative here will be outside of your function, whatever it is.
It'll be in the very, very, very front.
So it'll be outside your absolute value bars, or outside of your parentheses, or outside of whatever.
Just, yep.
If you're reflecting across the y-axis, it makes your x's negative.
And that one is one of these sort of situations. So
depending on what you have, it may not actually, if you actually have
much.
this, that doesn't really change anything. But depending on what it is, it could really affect things.
But
most
again,
of the
it's
time,
only x values that change.
Yeah, most of the time you will end up with a reflection across the x-axis. That one is so much more common than the reflection across the y-axis. I'm not entirely sure why, but I'm telling you it is. So if you had to guess x-axis. Yeah. But don't guess, just know it. All right, so
always know.
Example 2 says find an equation of the reflection of f of x equals 5x minus 9 over x squared plus 3 across each axis.
That looks really hard.
That's a pretty crazy function. Like, that's not a
Do
parent
we have
function.
to do long division on this?
No, all we're going to do is use our rule here.
Okay, if you say so.
If we are reflecting across the x-axis, let's do that first. What do we have to do? Whoops.
Whoa.
X-axis. What do we have to do? We have to make our y's negative. In other words, make your function negative.
So, okay, let me guess. Negative 5x minus 9 over x squared plus 3.
That is correct. So f of x, our new f of x, will become a negative in front, 5x minus 9 over x squared plus 3.
Is it really just that easy?
It is just that easy, because what's going on is this whole thing was f of x.
Right.
It wasn't some parent function hidden inside that we were trying to deal with. They told us what f of x was, which means we need to put the negative outside of our function. Outside of our function is bam, out in front.
Okay.
Okay.
I like it.
It's not on the top or the bottom, it's just out in front.
So there's no trickeration here.
No. Now, y-axis.
Okay.
We want to make our x's negative.
All right. Now this is going to be, pay attention, because Now there could potentially be some math involved.
Right.
Okay?
So our new function, if we make all of our x's negative, that means where we have x.
You put negative x in.
Right. And I'm going from the original here, not from what we just did to
Right,
get
right.
the x-axis.
From the original function, everywhere you see x, put negative x in.
An issue. You have to put negatives in parentheses.
If you don't, you're going to have, those will be points you'll miss when you shouldn't have. You'll get whatever was graded back and you'll be like, oh.
Silly mistake. Okay, so 5 times a negative x is?
Negative 5x minus 9. That's your topsies.
That is. Now, negative x squared.
That's negative x times negative x.
Which is positive x squared.
Righto.
So on top our negative didn't go away, but on the bottom it did.
Now,
so this is our...
That's a reflection over y.
Yes.
And notice we didn't go through and just change all the pluses and minuses
that's
around.
Right.
We did some math on this.
You have to do the x's only. Like we didn't change all the signs. We actually only changed one sign on the whole thing.
Right.
And it just somehow makes that flip.
Right.
Go figure.
That's what you have to do.
Yeah. Stretches and shrinks.
Yay.
Okay, so a horizontal stretch or shrink is where our graph is going to be stretched.
Or shrinked.
Or shrunk, yes, horizontally.
Like that bus on Harry Potter.
Like the bus on Harry Potter. A vertical stretch or shrink is where what we have is going to be stretched vertically or shrunk vertically. Now, at some point you may be like, aren't those like kind of the same things?
Yes,
like,
they are.
Like sometimes when we horizontally stretch,
we vertically shrink.
You talk about the vertical shrink,
Mm-hmm.
but our equation is telling us a specific way of doing it,
Right.
so that we know what the factor is we're stretching by.
Right.
Because just because you vertically shrink, you may want to know I'm vertically shrinking by a half. Who would want to know that?
Mathematicians.
And architects and all of them people would want to know that for sure. And so for horizontal stretches or shrinks,
Thank you, Ms. Teal.
That's the inside of our function. So that's
Right.
the super secret opposite society.
Right, which is now the super secret reciprocal society. So,
SSRS? That doesn't stand for anything.
Let's keep it opposite, I think. But remember, when we say opposite here,
we're talking about
mean
reciprocal now. Okay, we're not changing the sign. We're talking about reciprocating. Okay, so whatever's inside of our function, the first thing you need to do is flip it. Okay, so if you have 1 over 2, flip it and make it 2.
2 over 1.
If you have like 3, you flip it and make it 1 over
1/3.
3.
Mm-hmm.
And then that
what if
is
you got
gonna
like
help you.
3/3 or no? What if you have 2/3? What if you have 2/3?
Then when you flip it, that's 3 halves.
There you go. See, it's not hard.
So when you flip it, that's going to tell you the stretch or shrink. Because if I flip it and get 2, that's a horizontal stretch. But if I flip it and get 1/2,
that's a shrink.
That's a shrink.
Right.
Okay. If you look at it pre-flip, then it's going to be confusing. Look at it after you flip it, and then figure out if it's a stretch or a shrink.
For sure.
Vertical stretches or shrinks, they're my
Those
favorites.
are easiest. Those are the easiest ones to see in all the whole world.
Yeah, they're on the outside. They're literally multiplying your y values by whatever number it is.
So if I take 2 and multiply 2 by something like, I don't know, 3.
Yes, that's 6.
That's 6. That's 3 times more than 2, which was where I started.
Yeah.
That's up.
Yeah. So so whatever this number is on the outside will actually be either your stretch or your shrink. So if it's a 5 on the outside, you're stretching by 5. If it's a 1/2 on the outside, you're shrinking by a half.
Right.
All right, let's do this example.
Okay, let's do it.
Okay, this is worded kind of weirdly. Okay, so it's a good thing we're doing this together. Let C1 be the curve defined by...
y1 equals f of x, which equals x cubed minus 16x. Notice that here we're saying very concretely y equals f of x, which is equal to x cubed minus 16x. So this is a little bit of vocabulary for you, or maybe some...
something like
recognition.
That. Okay, and notice this is not exactly a parent function.
No, it's been manipulated a slight skosh.
But we can still do this. But we wouldn't necessarily ask you to graph this.
No.
Straight off the bat. So find the following equations. C2 is a vertical stretch of C1 by a factor of 3.
Okay, so we're going to look at the vertical stretch, which is the bottom situation here.
Right, we're doing 3 times our
f
function.
of x. Okay, that means 3 times everything that f of x equals.
Okay, 3 times everything that f of x equals. Well, f of x equals x cubed minus 16x.
Yes, and now you just distribute and multiply.
Right, and we'll call this C2
yeah.
for funsies because they called it C2. And so that's
3x cubed minus 48.
Nice math.
Every now and
with
then.
An X. Okay, that is our graph stretch with a vertical stretch of 3.
See, that wasn't hard.
That wasn't hard at all.
Now this one, pay attention because now
Maybe this will be tricky.
Be a little bit more.
C3 is a horizontal shrink of C1 by a factor of 1/2.
Woof.
Okay, so we're shrinking by 1/2.
Right.
And we're talking about the X values, right?
Right. The X values are having to get smaller.
Horizontal is talking about your X values. So what we do has to directly affect X.
Right.
So it's going to be on the inside, which means we got to super secret oppositely flip it.
Right.
So that what we're really going to do is
we're not working with 1/2, we're working with 2/1.
Yes. So I'm going to multiply the inside of my function by 2.
Right.
And this is our function way of writing it. That's what we have up here.
That's right.
I already flipped the 1/2 and I made it 2.
And this is why function notation is so important, because now we're saying the function of 2x. That means everywhere we had an x in original, every x now becomes 2x.
So where we had x cubed, now we've got 2x cubed.
Right.
Where we had negative 16x, now we've got negative 16 times 2x.
Right.
Okay, because everywhere that we had x, we got to put 2x. And we got to put it in parentheses because 2x cubed
is 2x times 2x times 2x.
And that's important. That can really be a deal breaker. Let me call this C3.
C3PO?
So C3.
Human cyborg relations?
Similar. It's a cousin of his, actually.
Okay.
8x cubed, and then 16
32x.
times 2, negative 32x.
Bamsies.
There we go. Ta-da.
Excellent.
Not too
Excellent
bad.
stuff. Okay, we're going to find the equation of the graph of y equals x squared.
That's a parent function.
Okay.
It's a parabola.
Yes, opening up. But we're going to look at it as it undergoes the following transformations in the order we've listed, and then does that order really matter?
Yeah, we're going to answer that question.
Okay.
So if we go through this in order, a horizontal shift 2 units to the right. Okay.
That's going to be inside parentheses because we're parenting x squared.
Yeah, our parent function is x squared, so we've got to be inside of the squared.
So x minus 2 because it's the super secret opposite society.
Correct. Then we're going to vertically stretch, and think of it this way. We're vertically stretching now what we've already got.
Right. Well, the function we have written needs to be vertically stretched.
Which means to put a 3 on the outside.
Because there's nothing else in there.
Okay.
You know, if you wanted to, you could put big brackety things to symbolize 3 times.
That now this is our function.
Yeah,
is that
that's
what
our
you're saying?
function.
Now this is our function.
That's our
but
function.
We don't have to have the brackets
we don't,
there. We'll
no.
find out. And then we're taking that.
And we're going up 5.
So that's a 5.
Fiver fever.
On the outside. Okay, so in order for us to figure out if the order matters, we need to do this the opposite way.
Let's do it.
Let's see if we get the same thing.
Let's do it. So,
okay. A vertical translation, 5 units up.
Now, that means we're taking
x
squared and we're going up 5 units.
Right.
Okay.
Now, this is our function.
Right.
Okay, this is our
That's
new
our function that we're going to vertical stretch by a factor of 3.
Which means we put a 3 on the outside.
Right.
Boom.
Okay.
Boom. That's not the same thing.
No, that's a different thing.
That's a different thing. And then when we horizontally shift 2 units to the right, you still are going to put parentheses for x squared.
Yeah, but it's going to look different, I feel like. Whoa.
I'm thinking it's just going to be
that's not going to be the same thing.
Yeah.
I feel like those are different things.
These are 2 different things. We could actually foil it out and stuff and actually figure out what it is. If you do that, the first one gives you, let me switch back. The first one gives you 3x squared minus 12x plus 17.
Whoa, how did you do that so fast? Oh my goodness.
I have the answers.
What's going on in that head?
Oh, don't touch my head. Personal space. We've been over this.
What?
Okay? All right, so no, those are not the same thing.
They're different. They're different things.
Because of the order we did it in, if we shift up and then we're talking about stretching, it's going to make it go up that much more.
Right.
Now, the only time this matters is if you're doing a stretch or shrink and a translation of the same type.
Right.
Okay? And it's really not as bad as it seems, because if they give you the function and like you're trying to graph it or whatever.
When they give you the function, it's easier to see what's going on.
Yeah,
I think.
Yes, than to write it like this.
Right.
So when they give you the function and it's got both of those things, you want to stretch first and then move up or down. Because if they gave us, you know, something simpler like this, if they gave us this and asked us to graph it, well, this 3 is closer to our x squared.
Right.
So we want to stretch it by 3 and then move all of our y values up 5. Okay, so the order can be tricky. The key is to like try to make connections as you're working through the homework so that, you know, you can learn when is this more important than this.
Right. And look for what we've shown you here. It might take a few repetitions of just working out the exact same problem over and over to understand it. You might not get all of this at one time, and that's okay. But you have to practice this so that the understanding will come.
Right.
Yep.
This is going to be so great. Example 5. We're going to sketch the graph.
You didn't even let me,
No, it's going to be great. So we're going to sketch the graph. This graph right here is f of x, BT dubs. Okay, that graph is f of x. We are going to sketch on our own graph the graph of 1 plus 2 times f of x minus 1.
All right, that means that whole, I can tell right now, first off,
yes,
the easiest 2 things for me to see.
Okay.
We're going to raise that whole graph up 1 unit.
Okay.
And we're going to slide that whole graph to the right 1 unit.
Okay, now let's make sure that our viewers at home follow the fact that this 1 right here, even though it's in front, it's still like we're adding 1 to our function.
Right.
Okay, so we've been saying like f of x with a plus 1 at the end, but it can be at the beginning as long as it's being added to our function.
Commutative property of addition.
Right, yeah, either way.
All right.
Either way. Okay, so I agree. And then the last part of that, which we haven't mentioned yet, is the 2 in front of f of x is a vertical stretch
by a factor of 2.
By 2. Okay, so the way we want to do this, there's multiple ways you could do it, right? You could do each of these things like one at a time.
Right.
You can try and do them all at once.
Right.
And it really just depends on how comfortable you are. I do suggest that we do our vertical stretch like right off the bat.
Yes, because then you just add 1 to that.
Yes. Okay. And so the only things, remember, that conflict are our vertical stretch by 2 and our up 1 can conflict. And which one needs to happen first? The one that's closer to our function, which is the 2.
Right.
Okay. So if we move...
Because we're multiplying our function by 2 first. That's what we're doing.
And then we're
moving
1.
up 1. Okay?
So
think about the whole multiply, add, subtract.
PEMDAS.
PEMDAS.
Is that what you're talking about?
PEMDAS,
the order of operations.
Yeah,
Please
order of
excuse
operation.
my dear Aunt Sally.
Yeah, except don't do it in that order, and we're going to show you later this year why that order doesn't always work. But you multiply, divide first, add, subtract second.
Yeah.
Okay?
So some points here that would be helpful to us, you know, just places where we meet, like crosshairs or whatever. And
like actual points, perhaps.
Yes.
So find actual points on the graph.
So this is like 0, 1 right here.
Right.
We want to multiply our y value by 2. That's a vertical stretch of 2.
0.
Huh?
2. Sorry, I was thinking the point. So 1,
multiply
0.
your y value by 2, so that gives us 0, 2. So that brings us up here. Brings this point up here. But then whenever we do this point, which is 3, 2, and now we multiply that y value by 2.
That's 4.
Okay.
Plus 1.
Well, let's just do I'm just looking at the vertical stretch right now.
Sorry, my mistake.
Just by the way.
Okay, all right.
Okay.
That's what you said.
Yes, I said that.
Yes, you
okay,
did.
so our vertical stretch now at 0, 0, that point doesn't move.
That doesn't change.
Okay, but here at -2, -1, we multiply our y value by 2 and get down here.
Right.
And so this pink graph is, if we just
curvy.
Sorry about that. our vertical stretch. Okay.
By 2.
And
now,
look, it looks vertically
It does.
stretched.
Yeah, because remember, you can't vertically stretch something that's flat. It just...
No.
You can't move it. All you can do is up and down. But you can't stretch a flat line up. That's just no deal. Don't do that.
I mean, yeah, it did move up.
But
it didn't change.
Yeah, we didn't stretch it.
Okay. So now if we do, now we could do up 1 and right 1 to me, like really easily. Just move each point up 1, right 1, right?
Right.
And so this point goes up 1, right 1, which is technically 2 tick marks for each. Up 1, right 1. This one, up 1, right 1.
Yeah, we're moving the pink dots.
Up 1, right 1.
Oh, looky there.
Up 1, right 1. Okay, and you should kind of be able to see what that graph looks like. So if I move it over to my new graph, I've got the point 1, 3, right here. I've got the point 3, 3, which is right here.
I can't see these, so it's a good thing you can see good.
5 with my young eyes.
0, 1.
0, 1.
That one I can tell.
And -1, -1.
Yes.
And
that's it. That's all you had.
That's all I had. And so then we would connect it with some straight lines.
That is the straightest line I've ever seen in my life.
Because I got.
Don't give away all our cool tricks. You're
and
freehanding
then it would
that.
go forever. Okay, so that is vertically stretched by 2, up 1, right 1. If you wanted to try really hard and do those all at once, you could, but just keep in mind the vertical stretch or shrink needs to come before that up or down.
Right. Multiply before add.
And then it doesn't really matter in this case when we shifted right, because y is kind of doing an independent thing from x.
Right. And this will be something, you know what might be a good idea? Pause the video.
Pause it right now.
Redo this problem. After we get done telling you this, then pause. But
pause it.
Redo the same problem on your own and see if you can match what we got.
Yeah.
Because it really will take a few tries.
Yeah, definitely. Takes a little, because we have this function, but we don't know what the function is, but we're supposed to do stuff to it. It's kind of a weird concept.
It is.
But you know what? It's a great day to be a bulldog.
It is a great day to be a bulldog. It's
always
a great day to be a bulldog.
Always a great day to be a bulldog. A code.
Code. It's a great day to be a bulldog.
Okay. Stretches and shrinks.
All right, let's confuse everybody.
Way to be pessimistic.
I mean,
drop pin.
Why?
Stretches and shrinks.
The crap stops here. You're gonna get it. It's gonna be amazing.
What did I just say?
You said don't make it hard.
I said and don't say crap either. Like, why are you always doing this? Stretches and shrinks.
You know what? I'm not gonna project my emotions here.
Good. It's about time. All right, horizontal stretch.
You're gonna get these, whether it's the last thing you do or not. All right.
Baby. Having a baby. You're not having a baby. What are
Giving
you
a
doing?
baby. Giving a baby. I like that.
You're not doing either.
We're going to the hospital to give a baby.